Yesterday, Francesco asked me to tell you something about the physical meaning of the deformation tensor. But since you have no time, you will not arrive to this result in this first hour this morning. So he asked me to switch on another subject. That is the representation of linear application through matrices. I have also spoke with Tomek, and he told me that matrix calculation is familiar with some of our you. For example, you know what is the determinant of a matrix. You know what is it, the row by column product. You know what is it, a matrix. You know? So a matrix, but also a column of number. A matrix is a table of numbers. A column of numbers is a column of number. And sometimes it is useful to use column of number to represent vector. In the same way, we use table of numbers, so matrices, to represent linear application. That is what you have talked about linear application in the previous lecture. And for example, if you have a frame of reference, which you have x and y are the coordinates, and you have a second frame of reference that you call x prime, y prime. You can associate to each of these frame of reference a basis. And generally, this basis can be represented as a unit vector along the frame, along the axis. And generally, to the axis that generally is called x, one associate the basis vector a1. When I use an hat, it means that this vector has a unit length. Associated to y, you have a second, the second vector of the basis. Here on the blackboard we have two-dimensional space, so we need only two vectors to project every other vectors. But these two vectors can be chosen in almost arbitrary way, not an arbitrary way, but almost arbitrary. One of these possibility to use this A1 and this A2. Another possibility is to use a unit vector associated to another frame of reference, for example x prime. And you have here A1 prime that is different from A1, from E1. And the second one is E2 prime. So in this way you have four unit vectors. A1, E1 and E2 are one basis that can be called B. And the second basis can be called D prime. Let us assume now that this angle is 30 degrees, and we want to represent a vector A that is defined in this frame of reference in this way. This is another 50 degrees. So one can say, what is the vector A with respect to the basis B? So this vector A is the length of A. For example, if we call the length of A, with respect to the first basis, to the basis B, one can say that this vector A is equal to the modulus, and then you have the projection of this vector along X, that is A, you see, cosinus of 60. This is the projection along E1, so here we have E1, and then also the projection of A along E2. Another A, and then we have here cosinus of 30, because if this is 30, this is 30, between X and Y we have 90, so here we have another 30 degrees. So this is, one can say this. And from the rule of the equilateral triangle, you know that the sum of the angles inside the triangle is 180 degrees, so this is 60 degrees. And so one can say that 1/2, if the length of this side is 1, this is 1/2. And so 1/2 is equal to cosinus of 60. And one can also derivate that this length is sinus of 60, that is square root of 3 divided by 2. This means that here the cosinus of 60, that is 1/2, so A over 2 A1 plus cosinus of 30 is it clear? Now, these are very easy passage, but if there is something that you don't understand, you need to tell me, because of course, there is nothing conceptual to understand, just to see what is going on. Here we have this vector, and the vector have a representation along the basis B in this way. You have the first component is A over 2, and the second component is A square root of 3 divided by 2. Well, that's the second component. But you can also say that this vector can be represented in another basis, the basis B prime. And you have that this is A cosinus of 30 E1 prime. And then you have also the A cosinus of 60 E2 prime. That means that here we have A this identity. This is a vector, this is equal to this, but also equal to this. This means, you understand?
Yes.
This means that if you want to represent the vector A with respect to the basis B, you need two numbers, A over 2 square root of 3. But if you want to represent the vector A on the basis B prime, you have another representation. So from this reasoning, you can easily see that a vector is not a column, is not represented by a column of number in n dimension. In two dimension is not represented by two numbers, because this is not enough. You have to fix the basis and then you say the two numbers. So the same vector have different representation in different bases. And the same occurs for linear application. Yeah, I have something to give an example. Let us assume now a linear application F. This linear application can be applied to a certain vector B. And let us assume to consider the following application. We have 2 B This is an example of linear application. You have a vector B belonging to some vectorial space. You apply linear application, and you write to another vector. This is a scalar product. That means that this is a scalar in square parentheses in parentheses we have a scalar, so a scalar multiplied by a vector is a vector, plus a scalar multiplied by a vector is a vector. So this is a linear application that satisfies some rules that I think that Francesco have already explained to you. That means that a linear combination of this B equal to L plus delta. The linear combination on this space is the same of linear combination of the other space. See? So this is the definition of a linear application. This satisfies this rule. This can be proved that the name is linear because you see that here is B appears only one time for every factor. This is not a definition, this is a definition. In books are written also better, but the idea to say linear is this one. You have black box, the linear application, you introduce two input, you have two outputs. If you introduce the sum of the input, you arrive to the sum of the two outputs. So now, an important tool in continuum mechanics is to find a representation of this linear application. In the same way as we represent vectors on one basis with the column of numbers that can be different if you choose the different basis, we will see that for linear application you can have a matrix representation. So you can represent this linear application with a matrix, with a table of number that depends upon the basis of the vector field here and the basis of the vector field here. So you know that an application, the application L is from a certain vectorial space to another vectorial space. So generally you have a basis for this vectorial space and a basis for this other vectorial space. That means that to define a linear application you need two bases. Two bases, one for B and one for W. If in continuum mechanics you have, for example, reference configuration and present configuration, the configuration called with the capital X and the configuration called with the small x, you remember, on the lecture, the previous lecture. And you can also choose the same vectorial space. So these two vectorial space can be represented with the same basis. Anyway, it is also possible to represent linear application with different bases because these vectorial spaces can be different. So the representation of linear application needs two bases that can also be the same, but this is a particular case. This is something to do to the fact that to represent linear application, you don't need only a list of numbers, but a table of numbers. Now let us see how to do this with this example. Particular, we can see the representation of the linear application L with the basis B. We can also see the matrix L with the basis B prime, the matrix L with the basis B prime B, and the matrix L with the basis calculated with the basis B prime B prime. Well, with the two bases that we have defined here, we can see four different representation of the same application. This is important, of the same application. Of course, the basis of a vector space are infinite, so they have infinite way to represent the same linear application. Having a tool in which you can represent vectors and linear application in different bases is very important for application, because in application you have, for example, direction that are privileged with respect to the other, so you need to have it is convenient to have one axis in that direction, maybe. So this is strongly related to also to simplification, because you cannot most of the time you cannot model a phenomenon only with one basis. It's not convenient. It's also you need more framework elements, and we will will see that these are also implications in the future. Let us see. Let us concentrate on this, and maybe for the next time to see if you have understood. You can use this. You can find the other representation. We will discuss if you don't get the result. Let us see the first one. So for the first one, what is necessary? It is necessary to have a representation of L on the first basis and V on the same basis. So it is important now to say what is E2 prime with respect to E1 and E2. For example, one possibility is the following. So we have E2 prime, but is equal to E2 prime with respect to E1 and E2. The modulus of E2 prime is 1 because E2 prime has this hat. So the modulus is 1. On E1 is as a negative projection, and this is 30, so this is 60. So you have cosinus of 60. E1, and for E2 you have positive projection, and you have cosinus of 30. Cosinus of 60 is 1/2, so this is minus 1/2 E1 plus square root of 3 over 2 E2. This is E2 prime. That means that here, then another thing that we need is to see, okay, V can be expressed the same way as we expressed the A that have two different representations there. But that representation are this EV and this EV prime are representation for a given vector. Generally, one vector can be represented with a certain value on the first basis, or another possibility is to choose another on the second basis. You can say this V2 prime, E2 prime. So the same vector have V1, the column V1, V2 in the basis E1, E2, or the column V1 prime, V2 prime on the basis E1 prime and E2 prime. Sometimes I will avoid this, but for sure the Isola will not do. But he will use this notation. This is VI EI. When I say this, when you see two indexes, repeated indexes in the same product, it means that you have to say, you have to calculate this with, you have to know how this index, what is the range of the index I. In this case, the range is 1 and 2, and then you calculate this with I equal to 1 plus the same with I equal to 2. So then you can arrive at this result. This is a shortcut This just to maintain a common nomenclature, so that this linear application can be seen in the following way. For example, V scalar E1, what is it? In this representation, take this representation, the first one. What is V scalar E1? V1, not V prime. See, V scalar E1, what is it? Is V1 E1 plus V2 E2 is V scalar E1. This is equal to the first, equal to V1 E1 scalar E1 plus V2 E2 scalar E1. You see? This is the rule of distribution of product with respect to the sum. But if this vector is unit, this is the length, the square length of the vector. 1 to the power 2 is 1, so this can be cancelled. If the basis is orthogonal, means that the two vectors are at an angle of 90 degrees. That means that E1 and E2 are 0. E1 scalar E2 are 0. So it means that V scalar E1 is V1. And V scalar E2 prime, what is it? Your opinion? Sorry? V2 prime, because this is prime. That means that if you use this representation, you don't go very well. If you use this representation, then you see that this is V2 prime. But if we need this representation of the linear application, we need to see this vector and the external vector L of V, both with respect to the metric, with respect to the basis B. So it is convenient now to you to express E2 prime with respect to E1 and E2. So L of V is equal to 2 D1 multiplied by E2 prime. That means minus 1/2 E1 plus square root of 3 over 2 E2 plus 3 E1 multiplied by this. But this is what is it? V scalar the vector, the unit vector E2 prime, that is the same here. So minus 1/2 E1 plus square root of 3 over 2 E2. See, the parentheses are see that this is not a vector, this is the component of the vector. This is a scalar, this is a vector. This is a vector multiplied by a scalar. You see here a vector, but then you have a scalar product, so So you can say that this is equal to minus V1 E1 plus square root of 3 V1 E2 plus 3 E1 multiplied. I will change this square, the external parenthesis in squared parenthesis. So here we have minus 1/2 V1. Why? Because V scalar E1 is V1. Then you have plus square root of 3 over 2. The 3 is kept V2. This is equal to E1 multiplied what? Minus V1, then minus 3 over 2 V1 plus 3 square root of 3 over 2 V2 plus square root of 3 V1 E2. This is L. So our target is to find the representation of this linear application with respect to both bases. What? Okay, this minus 1 minus 3 over 2 is minus 5 over 2. V2. No, this was V1. V1. So this is now very simple. What is the idea of this matrix? The idea is the following. You know that if you have a matrix, you have some component of this matrix, and you apply this matrix to a vector. You know what is in the result? This is, you have to do the row by column rule. It's A, E, plus B, F. This is the first component of the second column. This is the first column. We have another column. The first component is E, A, E plus B, F. And the second, C, E plus B, F. So what is the idea of this representation? You project, the idea is the following. Here we put the matrix of the representation matrix of the linear application of B with respect to the two bases B and B. Here we put the vector V, but not a general vector, because we need here not a vector but a column or number. So we need a basis. Which basis we choose? We choose this one, B, and here the linear application L applied to B, that is another vector, but we don't need a general vector here, because here we have a list of numbers, so a column of numbers, and so we need a basis. Which basis we choose? We choose the other one here. But now in this particular case we have the same basis. And so here we can put instead of E, we can put the representation of V with respect to the first basis, that are V1 and V2. I have erased not here, you see. On the first basis, V, that has the V1 and V2, the components are V1 and V2. So instead of write E and F, we write V1 and V2. So E here, this is V1, this is V1, and instead of F, we write V2. So we have chosen here. The second, we have to choose something. We can choose the representation with respect to B. But here we have, because we have the representation of L here. This is the first component, this is the second component. That means that here we have the first component, we have minus 5 over 2 V1 plus 3 square root of 3 over 2 V2, and the second component is square root of 3 V1. You can impose now these two equations, this equal to this, and this is equal to this for every V1 and V2, because a representation should be good for every vector V. So the first, you can see. So the first equation is A V1 plus B V2 equal to minus 5 over 2 V1 plus 3. Okay? The second one is C V1 plus B V2 equal to square root of 3 V1. But this should be satisfy this system for every V1 and V2. This is the symbol for, that means for every V1 and V2. That means that here, for example, if we want that this is equal is for every V1 and V2. For every V1, it means that also for V1 equal to 0, and also V2 equal to 1. That means that V is equal to 0. But if D is equal to 0, this means C V1 equal square root of 3 V1. For example, if V1 is different from 0, you have also that C is equal to square root of 3. From the one, you can also say that if V2 is equal to 0 and V1 is equal to 1, you see that A is equal to minus pi over 2. And if V1 is equal to 0 and V2 is equal to 1, you have also that V is equal to 3 square root of 3 divided by 2. That means that this representation is also found. That is what we want at the beginning. So this representation now is very simple because we have minus pi over 2. B is 3 square root of 3 over 2. C is square root of 3. And D is equal to 0. So this is the representation of the previous form that I have here. So I have to go. So our linear application was the following: 2 d scalar into 1 multiplied by E2 prime plus 3 d scalar E2 prime E1. This was the definition of the linear application. Into the basis BD have this matrix representation. That is very important, for example, in computer application, because computer treats numbers, so you need to assign a basis. But maybe from the theory you have a representation of your linear application very strange, because in the representation you have different vectors that belongs to the reality. So it's not necessary that it is straightforward, the definition from the theoretical point of view. But then, in order to apply to have the matrix calculus, you need a matrix representation of this. You know the basis B and B. You want to use the basis B for the first basis, for the first vector space and the second vector space. So you need this matrix representation. That means that if you have any vector V, you simply do the rows by columns, and you arrive. You know the result of this linear application very easily. Okay? So I think that I have finished the time. What is the time?
Mezzogiorno e 20. Mezzogiorno e 20.
I think. Okay. Now, for your exercises, you can arrive to these other three matrices. If you don't understand, ask me or ask Francesco. It's the same. But now, I want to give you a very important example of a linear application in continuum mechanics. In this 10 minutes is important. Is useful for you to see this. You have seen the potatoes. Then every point of these potatoes is called capital X. Then you have the placement for a certain time. For a given time, you have a placement. You have the formed potatoes, and the image of this placement of this capital X is small x. When one says say x on capital X and small x, you intend a vector. Then if you have a basis, you have a representation of this. And this is called the current configuration, generally the name is C. Now, an important tool is to see what happens in the neighborhood of a point. So it is important to see, okay, we have key that is a function of x. Now we have that is equal to small x. Now I intend here as a vector. These are vector. They do not become from a vectorial space, but anyway, this is are vectors. And now let us see what is happened to a vector, a point in the potatoes in the neighborhood of this x. For example, if we call this x, this point, capital X plus dx, in order to see that they are close to each other. What is the image of this point? We have to apply the same placement, because we make a picture at the same instant of time, and you arrive to another point that is small x plus dx. So you can say that capital X of x plus dx is equal to small x plus dx. Okay, but this placement, if we are interested only in on what is happening in the neighborhood of the point, so in the neighborhood of the point, you can develop in series, in Taylor series. You know what is a Taylor series? There is someone that do not know what is a Taylor series. Everyone knows? So generally you have a function, the function placement, and you can develop it. So you can calculate the same function in the centered. Let us develop this function centered in x. We have this plus the derivative of t with respect to x multiplied x plus dx minus x, so dx. You maybe have done this Taylor series in one dimension. In more than one dimension, what do you have? Let's say the following. One have here we have key of x, but key of x is equal to small x, isn't it? So instead of key of x, we write small x. So here we have small x and small x. So we can erase this, but we can arrive to the following. We can arrive that dx is equal to this animal, the derivative of t with respect to capital X, multiply this animal. This is a Taylor series function, so here you should have plus corrections, because when you make a Taylor series expansion, you have some error. And this error are of the order of dx to the power 2. That means that if you choose these points far and far closer, more close, then this error is more and more small. What does it mean, this function? It means that if you take a vector in the initial configuration, this vector, because if this is x, capital X, and this is capital X plus dx, this vector is exactly dx. If this is small x, and this is small x plus dx, this vector is exactly small dx. This is dx, and this is dx. But how they are related? Well, if you have potatoes, you deform it somehow through the placement function t. This, so the atoms, the particles along one line, very small, are among one segment. The particles among one segment, they are replaced into the particles on another segment, the current configuration. They have the same orientation, they have the same length. These are something that are important to know from a continuum mechanics point of view. And these two are related, these two vectors are related to this matrix, to this linear application. For example, if you have that x1 is equal to capital X1 plus epsilon x1 and x2 is equal to capital X2. You have your potatoes is a square at the beginning. If you represent the placement function in this way, it means that you have already introduced a basis function. Let us assume, because of the geometry of our body, that E1 and E2 are here. What does it mean, this? What is the final shape of this function? It means that here you have this point have the coordinate x1. At the end of the deformation, this point have a coordinate x1 plus epsilon x1. But the coordinate in the coordinate in the x direction are changed. The coordinate in the y direction are not changed, because at the beginning was x2 and the end are x2. That means that here, if we choose also the origin here, just to have more for simplicity, so this is E1, this is E2, it means that these lines remain the same, because these lines have a coordinate x1 equal to 0. It means that at the end also have the coordinate x1 equal to 0. If here the coordinates here is 1, at the end of the deformation you have the small x1 is equal to 1 plus epsilon. What here? So the final shape is not anymore a square, but it is a rectangle. The height of this rectangle is 1, And the basis is not anymore 1, but 1 plus x pi, plus x pi, epsilon. This is epsilon. What is this linear application that we are talking about? The linear application is the derivative of t with respect to x, capital X. Is exactly the same matrix that dell'Isola have introduced in the first lecture when you saw the change of variables. So here you have the derivative of k1 with respect to x1. Here the derivative of k1 with respect to x2. So the first one is equal to 1 plus epsilon. This is the derivative of t1 with respect to x2. The derivative of t1 is this one. x2 is not present, so it's 0. The derivative of t2 with respect to x2 is with respect to x1 is also 0. And the same with respect to x2 is equal to 1. So this is the representation of displacement. So is the representation of this matrix that is called matrix of deformation. Deformation matrix. The reason I called it another way, with another name, I don't remember I don't know the name that here is used, but also the matrix of deformation is also called. Sometimes it's called with the letter F. And this is a nice example. We will see that epsilon represents the elongation with respect to the E1 direction. The elongation in this case with respect to the other direction will be 0. Then there is another way to measure the deformation that was also introduced by dell'Isola. That is how the angles between two different lines change through the deformation. In this case, for example, these two lines remain orthogonal. So this is a prototype in which this share is not occurring. But there are other examples in this share will occur. Almost for these two segment lines. In other maybe lectures or you will see an example for this. But I wanted to tell you this because what we told in the previous case, in the beginning of this second lecture, is related to continuum mechanics, for example, through this linear representation, through this linear application. It is the matrix that is the linear application of F. Okay? We will see next time. There are some questions?